My name is Boaz. I'm going to talk about authentication in the microservice world. So first, let's start with who am I? I'm a linguist by education. My programming is self-taught. I had a short stint being in charge of adapting legacy software for passwordless authentication that was used in the Israeli Digital Government Authority. That was back in 2010. They were pretty advanced back then. And since then, my focus was on authentication and cryptography. So I'm coming from the programming side, not from the penetration testing side. Currently, I'm in charge of the authentication architecture in a major Japanese IT company. And here I'm going to talk about what was before and how stuff changed and how do we deal with authentication in the microservice world that we have today. So if we start once upon a time, you see that authentication was simple. All we needed was HTTP cookies. And the flow was basically like that. You log in, authenticate, the server sends back a cookie, and the server keeps getting the cookie with every request from the browser, and it trusts that cookie. And the cookies were usually stored in a database. You could also store them in memory. You basically store some data there. You get an ID that is mapped to that data, and that ID becomes the cookie. And this was all usually handled by the framework, like JSP or ASP, or Ruby on Rails, or even by the language, like in case of PHP. So it was quite easy. There were threats, of course, and it was easy to make mistakes, and people did with this type of authentication. But most of the threats back then, they did have proper solutions. So you could say that the biggest threat was that people did not use HTTPS everywhere for a long time, but the moment you started using HTTPS and putting HTTP only cookies and not putting these session IDs inside a cookie, inside URLs, it was pretty easy to protect that. There are a few other smaller issues like session fixation, timing attacks, and things like that, but they all have solutions. But I'm not going to get deep into this world because what happened in the 2010s is that everything changed. SPAs started replacing server-side apps, and microservices started replacing monoliths as well. So instead of this one monolithic server that receives cookies and can authenticate and can have its own database, you started having a much more complex architecture. And another thing that was already starting even before that is the rise of APIs. They were already a thing because of mobile apps and other services that were talking to each other in 2010, and they just kept becoming more and more popular. You started getting things like this. This is a diagram that was presented by Netflix about 6 years ago. Netflix were a bit of an early adopter when it comes to microservices, but this is how a lot of companies look like today already. Deep layers of microservices talking to each other, sometimes some gateways in front, but there are multiple access points. The communication patterns, the lines between the services, where you see traffic flows are very complex. And in this complex landscape, how do we deal with authentication? So let's first talk about what would be the ideal requirement for a solution. And we're already saying here by ideal that in the real world there will be some trade-offs and you might not get all of these things together. But at least we want to have that picture in mind. So first of all, we don't want to have a shared database. That doesn't work the moment you have hundreds of different microservices. We want to have defense in depth. That is, we don't want to have a situation where services have to fully trust each other. They might have a certain amount of trust, but we need to authenticate them to each other. So you don't have a service, you don't suddenly trust anyone who calls you. And you want to make sure that the users that they claim to be representing, for instance, when they're doing some operation, are actually the users that really logged into the system. And you want to implement the principle of least privilege. This is highly related to defense in depth. Basically, you don't trust all the services, because if you trust everybody completely, then it's enough to hack one service to really destroy the entire system. So you just need to attack the weakest chain in the link, the weakest link in the chain. And this is where the principle of least privilege really comes from. It's a principle that is based on this kind of defense in depth. And you can simply say services can only access whatever they need to access, but that needs to be enforced, right? So we want to prevent them from having access to things they don't need. That's in the realm of authorization. But in the realm of authentication, we want to prevent them from being able to claim that they are any users, any of the users, or they have access to any of the resources. So that's a bit complex and interesting. The last thing here is performance, and that's something that's very hard to get together with all the other principles. We want to minimize the amount of network calls and DB queries, so the latency becomes lower, because there's already high latency when you have deep layers of microservices. The bread and butter of our solution is session and tokens. But what are sessions and tokens? So the terminology is not always quite clear. So I'm going to have to clarify the terms that I'm using here. Sessions are basically just objects that are maintained. I'm using the word maintained here, not stored, on the server side. And they contain the authentication state of the current user. That's a very abstract definition. But the idea here is that they really contain some properties about the authentication state. And the very minimum, the properties that they store include who is the logged in user, some ID, and an expiration date, when the token expires, because you don't want them to last forever. And sessions should also be revocable. We need to revoke them in cases like when the user logs out, or when they have, for instance, lost a device and they want to disable the sessions that have been created on that device. And this revocation requirement introduces a lot of challenges, actually. So how do we use sessions now? So we need to have some mechanism that lets the client identify the session to the server and lets the server verify the session that the client is using. By client here, when I'm saying that, it can be a web browser, it can be a mobile app, it can be an IoT device, it can be anything, right? And it can even be another server that is another service in your product that is working on behalf of the user. The session identifiers, another term here, are basically just strings that identify the session on the client side. The client must be able to store them securely, because these strings are usually secret, right? We don't want them to be stolen. And that means, for instance, that we cannot put these session IDs in URLs as people used to do in the past. And these session identifiers should also be something that you cannot forge or tamper. So if, for instance, we have random IDs that represent something in the database, then this needs to be cryptographically secure. And if they contain data by themselves, and we'll get to that in the next slide, we need to encrypt them and authenticate them and use cryptography to prevent tampering. So we want to also prevent tampering, not just by clients, but also by unprivileged servers. So there might be a server that is passing this information and a gateway in the middle, any server that we don't want to deal with that data because of principle of less privilege, right? We want to minimize the attack surface. So these servers should also not be able, ideally, to tamper with the session. The last thing, we need to make sure that expired or revoked session IDs are truly revoked. This sounds obvious, but I've seen many implementations with cookies, for instance, where when the user logs out, the cookies are just deleted from the browser. So, of course, if somebody managed to steal the cookies before, they can still use that. So this is a vulnerability, right? So revocation needs to be real, not fake, not just a UX thing. So now that we've put down this list of requirements, quite complicated one, let's start by looking at the different ways that we can structure the session identifier. So I think you're all aware of this probably, right? Everybody aware of stateful versus stateless sessions. These are very common things nowadays. I talked before about the traditional cookies. These are stateful sessions. They have a unique ID, it's usually very short and easy, content escaped in database. Revocation is really simple. You just delete the session from the database. You just delete a row. And it's not really quite secure because you cannot know it if you don't know what's in the database. As long as your ID is strongly random and you do all the protections necessary. The main issues that it has is that you need DB access on every call. So this hurts scalability. And this also hurts distribution with microservices. And then you have stateless sessions, or obviously became more popular nowadays with microservices. So the idea of a stateless session, you use cryptography. You have a payload that contains all the information that you would put in a database. You sign that payload. You optionally even encrypt it. And performance is great, right? As long as your cryptography algorithms are good and don't require too much CPU. It's very easy to scale because there is no state, or there is a state. The state is in the session itself. All of the state, it's not really stateless, but the state is completely included in the session string. And that means you don't require any database and you can use it all over the world without having to replicate anything. There are issues with that though. One is that revocation is hard. How do you revoke these things? There are ways, but it becomes a lot more complicated. And cryptography must be secure because before you didn't even have to think about cryptography. Now you do. And cryptography is actually not that simple, unfortunately. So we have cookies and tokens. And we already talked about cookies. This is the traditional mechanism for storing this session string. So that would have been just a session ID that is stored inside a cookie. But the main trait of cookies is both their greatest strength and their greatest weakness. That is, they are implicit. They are associated with a domain name and they are always sent to servers on that domain. And you can't control when a cookie is sent. So this is not always good, and not for performance because there's a lot of overhead if you, for instance, have a lot of images, but also not for security. This is, for instance, where most of the CSRF vulnerabilities are coming from. They are related to sessions where you are authenticated with cookies. And to do CSRF protection in general, what we do, we add a CSRF token. So we really add a token, an explicit token, to protect the implicit cookie. And tokens, they became popular with APIs, so they are the other option, right? You explicitly send that session string in a header. And this is really great for APIs because you have full controls. You can switch tokens, you can send tokens that do different things, and you can choose when to authenticate and when to use anonymous APIs, for instance, which are not authenticated. The main issue that we have with tokens on the browser, where you can choose between them and cookies, is that they are not safe against XSS, right? They must be accessible from JavaScript because we need to send them explicitly in a request. And that means that they are less secure than cookies, which we can set to HTTP only in these cases. And you also cannot use them to protect HTML resources that are things like images, for instance, that are linked from HTML. So if you have this kind of thing, like an image that is in a private album that you want to do with regular HTML, or you want to have a media content download, that's something that was purchased just with a link, then you might want to use cookies instead of tokens. There are other ways too, but tokens will not help you here. And since neither tokens nor cookies are perfect, you usually end up using both. So it's just important to think that they are used for different purposes and not that tokens have completely replaced cookies. So for instance, you'd use tokens in general for all API calls, backend to backend calls, single page apps, mobile apps, a lot of things, but you would use cookies for things like XSS protection, for login flows, and in general, like the main login session or SSO session if you have a login page. And you would use cookies also for restricted access to static resources, at least one of the options. Now, another interesting property of tokens is that they're not really usable for just sessions. So it's a bit tangential to our topic, but you can use them for many other things, like pure server-to-server authentication where no user is involved is one thing, but also a proof that something that has happened, like SMS verification has succeeded, or you can use it to rob sensitive data, like credit card numbers or database password. And instead of giving the data directly to a service, you just give in a token, and there is something else that manages this data and uses the data. So this is used a lot, for instance, in PCI DSS compliance. So we actually use token a lot for things that are a bit tangential to authentication, but are very powerful. Tokens can also be constrained and delegated, and that's a very interesting property. Because if you look at traditional session cookies, the client cannot hold multiple cookies for the same server, because you only have you cannot choose which cookie to send explicitly. But with a token, you can have different tokens that have different permissions, for instance, and do different things. That also means that together with the possibility of manipulating tokens. So this can be done either by sending the token to an API and requesting the API to change the token or constrain the token, or by using cryptography. You can have tokens that you can put extra constraints on the token. For instance, this token is limited only for these usages, only for these scopes, only for these resources. And then you can delegate that to another service. And that service will have restricted access. And this is a very powerful mechanism that allows us to implement the principle of less privilege. Now, we talked about stateless token already, and this is where I think beyond the introduction, we get to the main content of this talk. So let's start with a review of the token formats that are out there for a stateless token. And this is pretty important because there are many options out there, and the popular ones are not necessarily the best ones. And that's an understatement. So if you talk about popular formats, obviously JWT, or JWT as it's often pronounced, is hands down the most popular format today. It is far from being the oldest one, but it got the best standardization push in the past, and it just caught. And it's a mandatory part of the OpenID Connect standard. So if you're using OpenID Connect, which a lot of people do to connect to many things, you pretty much have to use JWT at least for this part. The problem with JWT is that it kind of sucks. First of all, the cryptography that is not really, let's say, cutting edge. There is only one symmetric algorithm, which is perfectly safe, but a bit slow. That's a HMAC SHA-256 and other versions of SHA. But it doesn't get any encryption as well, right? Which is a bit of a weird choice. If you have symmetric tokens, the only reasonable, let's say, entities who can verify the tokens, they hold the key. So why make the token contents public? Like, it's just introducing a weakness where there's no point. Yeah, you can make everybody, make the token contents public so clients can read the token and contents, but it's no use because they cannot verify that this token is valid. So this is a bit of a weird choice that nobody else does. And they also allow you to use weak keys, but it becomes worse when you look at the public algorithms. Like they have RSA and ECDSA. Both of them are old and they have weaknesses. They only support like weak curves, etc., etc. Both of these are not really good options. There is new signing scheme that was added later than the core, which is using ED 25519, and that's a good modern algorithm for signature. It doesn't produce huge signatures like RSA. It is not slow on either signing or verification like both RSA and ECDSA. It doesn't have all the weird weaknesses that they sometimes have if you use the wrong key, if you use a weak key. You cannot do these things with this. So it's pretty powerful, but it was only added later because I guess it wasn't enterprisey enough. And unfortunately, not all the libraries support that. So the real problem with the JWT is that you have all these different options. All of them are supported in the same time. Actually, the spec requires you to support all of this algorithm, including an algorithm that is called algnon. So if you follow the spec of JWT, you must accept tokens. You must let the hacker take a token, modify the algorithm to algnon, which means that we don't verify the token, and it must be accepted. So actually, according to the spec, you must trust any token that is sent to you. The spec is that bad. And at the beginning, almost all the libraries had this vulnerability until they realized how bad it is. They closed it down and now everything is fine, right? Well, we can, for instance, let's say you have a public key and a private key, and you're accepting RSA tokens that are assigned by the private key. I can still take the algorithm header and change that to HMAC. And then I can take the public key, which is, again, public. It's published on a URL. I can take that key, sign the token with it using HMAC as a symmetric key with the same binary sequence. And I just change the algorithm to HMAC, and the token will be accepted. There are lots of vulnerabilities there. So really, like, my recommendation is not using this thing. or if you're using it, you have to be very careful in using it safely. Luckily, there are standards that try to do better. So we do have Passeto, which is just an IETF draft, unfortunately, but it tries to fix all of these issues. First of all, you don't have full algorithm flexibilities. You cannot use and choose any algorithm you like. You just specify a version, and that version is tied to a certain algorithm and the keys that come with this algorithm. Now, the thing is, when you verify, and this is part of the spec, you have to specify which version you are expecting. So you only expect one version in general, unless you are doing a transition. And then nobody can try to do this crazy algorithm switcheroo and fool you. The algorithms themselves are also stronger and more misuse resistant. The claims are the same as JOT, so they are compatible. The main issue that I see with this is that there are a lot of versions right now because they kept fixing minor vulnerabilities and try to improve. So it's a bit confusing which one to use, but usually the rule of thumb is you take the latest version, and which is right now v4, and you avoid old versions which are there for people who need weaker algorithms that are FIPS 140 compliant. So yeah, there are other formats out there too, but you can safely ignore most of them. Like there could be older formats like Fernet or various variants and extensions of JOT that are less popular and don't provide you anything really better in terms of security. Now, if you really want just a simple stateless token that encrypts a bag of data, I think the best option is currently Passeto. Or you can use JOT again if you really must, but you really have to be careful. Now, there are things that go beyond that and are interesting. So the most well-known one maybe is macaroons. Anybody heard of macaroons? So macaroons are really interesting because they add one very strong idea, which is offline delegation. With macaroons, you can add caveats. Caveats are the same as claims in JOT, like just attributes of the token. But all of these caveats are supposed to be constraints on the token. At the beginning, you generate a macaroon that is all powerful, has no caveats, doesn't represent all users, all scopes, all data, everything. And then you can add caveats to it. And you can add the caveats offline. So the client can take a macaroon, add caveats to the macaroon without knowing the secret key and without being able to sign it. And then it can send the macaroon with these caveats. And the caveats cannot be removed because they are the cryptographic key that was used before is not there. Basically, the idea is very simple. You're just using a chain of hashes, and the last hash or HMAC signature serves as the key that you're using to add the next caveat, and then you remove it from the macaroon, and only the original server can verify the entire chain of caveats. But the cool thing is that nobody can remove a caveat that you added because you removed the previous signature that was used to create that. So these are very powerful. You don't need network to add things, and it enables a lot of cool things. Like you want to do a proof of possession, you want to sign request. You can just take your existing macaroon and add a caveat that contains the URL, the method, and maybe even a hash of the body of the request, and that's it. You've got a request signature mechanism. There are downsides to these things, however. They are not all powerful. So first of all, one very big issue is that there's completely no standard for caveats and or attributes, if you want to say, except for maybe expiry. There's nothing in the standard. They also don't support encryption. This is, again, like just signature. There's a weaker library support. They do have a lot of libraries nowadays, but it's nowhere as far, as you get with JOT or even Passeto, which have libraries for everything. And one very big issue is that they are symmetric only. So for microservices, a lot of time you do need to use some asymmetric mechanism. Here with the symmetric only property, it means that yes, everybody can add caveats without network access, but to verify the macaroon, you must know the secret key. And if you don't want to distribute that secret key to everyone, then you're in an issue. You still need a network call to be able to verify them. And there you see like even crazier and more advanced things. So you have biscuits. This is a very ambitious project. First of all, they are asymmetric. So that solves one of the issues we've seen with macaroons. And the second thing, they do have a full specification for a caveat language. And what's more, that caveat language is based on datalog, which is a Prolog-like logical language. So you basically have a very powerful language that specifies logical constraints on what can or cannot be done. And you can run a logical resolver that basically runs an action and say, can I do it based on the constraints that are included inside this thing. Unfortunately, these things are even more complex. The learning curve for that stuff is huge, and they're also very new. The library support they have right now is minimal. So you basically have Rust, Haskell, and an unmaintained Java library for version 2, and a few bindings for the Rust library that is compiled to WebAssembly or a binary. So unfortunately, they are not very usable, but this is a very interesting concept. And it's also a very big revolution, so it will probably be hard to adopt. So now that we've seen like all these formats, let's look at another thing we need to take care of, and that's key rotation. And this is something that a lot of people miss the first time they implement tokens, stateless tokens. We must be able to change, to rotate keys, because we must have a way to deal with compromised keys. And these things can happen, right? The key gets compromised. And the thing is, if you're waiting for a key to be compromised and then as an emergency operation you try to change it, a lot of things may break. You don't know because you've never done it before. So there's a saying with regards to this kind of thing in tech that you want to keep your joints well oiled. With TLS, they saw that when they upgraded from TLS 1.2 to 1.3, there were some extension mechanisms that they tried to use in TLS 1.3 in the earlier draft, and it failed. Like all the middle boxes and the routers blocked everything because these things have never been done before. So these features were not implemented, even though they were in the spec. And this is the same thing. If you don't rotate keys regularly, then something will break. And then that's why we do want to implement key rotation. Unfortunately, it is something that is supported by all these standards that you've seen before, but it's not mandated by them, and it's not even like there are not even good guidelines for how to do that. Now, all of these standards usually have some mechanism like a key ID, something that identifies the key. And you can use the library and set it to accept multiple keys at once. And the trick is usually you go with something like a free keys scheme. You have a previous key that you used before for signing. You have the current key that you're using for signing. And you also specify the future key. And this is the key that you're going to use next. And every time you rotate key, you take out the previous key. You make the current key previous, you make the future key current, and you add a new key that you generate. And the previous key is going to be supported for a while, and you set your rotation timelines to make it sure that it's enough to verify all the previous tokens that have still been using this key. Now, let's go to how microservices actually verify the tokens, right? Because that's also interesting. We have this format, but and we have stateful tokens, but that's not enough. So we were using OAuth. Everybody knows OAuth here, right? I guess. But everybody at least seen it. This is a mechanism that we're using to do the initial authentication and get an access token. And after that, auth specifies that you can use this access token in the authorization header and authenticate to a service. But auth is very simple. It was written in the monolithic age. So auth is talking about one resource, one authorization server, which does the authorization, has the login page and everything, one client, which receives the token, and one resource server, which is the API that the client is sending the token to in the header. And there is only one resource server in the specification. Now, the servers in auth are a logical entity. Like in many implementation, the authorization server and the resource server are the same. And in theory, like there's nothing that says like, the resource server, there can be multiple microservices that are all counted as the same resource server, and we send the same token to them. But then how do we verify it, right? If everything is one monolithic service, that's very simple. It can be a database, it can be a key that is within the service, but we have a lot of options with different trade-offs when we deal with microservices. So one option is you have an introspection endpoint on the target service. And that endpoint in the authorization server, all the servers that receive the token, they just send the token to the introspection endpoint, and the authorization server checks on a database or use the secret key. And this is something that is also encoded in the standard RFC 7662. So it's simple, standard. It's got good defense in depth because all the token validation is controlled by the authorization server, and nobody can forge tokens. But it's got a network call that adds extra latency, and it also has a single point of failure on every call added. In every call, we depend on the authorization server, which is pretty problematic. Another option that you sometimes see is saying, okay, we are just going to distribute the secret key we were going to use symmetric token. We will just distribute the key to all the servers, and all the servers will be able to verify that by themselves. This, of course, requires stateless tokens. It won't work with stateful tokens at all. And it is easy to implement in code. It has a near zero latency, but you need to distribute secret keys, which is hard. You need to distribute them securely. Defense in depth is really bad because everybody can forge tokens now. All the servers can do anything. And you still probably requires to have some library to standardize the way you validate them, because especially if you have multiple claims that you need to care about, you need to make sure that all the services validate them in the same way correctly. Otherwise, you might run into issues and you will have vulnerabilities. And that is still a bit of a problem if you have different services written in different languages. The other option that is slightly better usually is using a public key signature. So here only the public token, public key is shared to the different resource servers. And this still requires stateless tokens. It has near zero latency. The difference is that you need to use a fast algorithm. You probably cannot use JOT, right, or the standard algorithms in JOT. You need to use something that is faster because RSA and ECDSA are slow. You have good defense in depth now because resource server cannot forge tokens. But you still have an issue, which you have with other options as well, is that the resource server can use their token because they receive the same token. The token is the same. We say everything is a logical resource server. So the resource servers can still use their token, to access other servers because it's all the same token. We don't really constrain this token to a certain service, and that's an issue. We cannot use encryption with this because it's a public token, and this is still something that requires a library. The next option that can be used with other things and simplify things a little is having a token verifier. Usually you'd use it with the public signature thing. So you, instead of creating a library, you just create a container that is running in the sidecar, in the resource server, and this container basically encapsulate all the verification logic. And then you can standardize things much better without compromising and having to write a library for each language. And the last option in this realm of one resource server things, which is used by a lot of services, I think, is to have a big API gateway that exposes all your different services. So nobody is able to call the service directly. They have to call from the API gateway. And you have tokens through the API gateway. The API gateway also includes an authorization module, so it issues the tokens and verifies them. After it verifies a token, it takes the payload out of the token and it sends all the relevant fields, usually in HTTP headers, like here, to the resource server. So the resource server knows who is the user, when the token expires, which scopes to use, etc., etc. A lot of things are simpler with this. The resource server needs to do almost nothing besides parsing HTTP headers. But the main limitations here is that you really only able to access these mechanisms, these things safely if everybody have to access through the API gateway. You cannot have servers directly accessing each other because then they can just send HTTP headers and pretend to be everything. So you need to put firewall rules to prevent anyone from doing that. And then you have a single point of failure with the API gateway. So yeah, you can see these things here. And I think...
Don't worry about timing.
Okay, yeah, I have one more... So I have one more topic where I'm trying to get, which is service-to-service auth. So I did talk about this thing, but we still didn't get to how we really implement defense in depth, where servers are able to talk to, services are able to talk to other services and have restricted tokens. Right? We can give restricted tokens to services so they cannot do everything, but they can do something on the behalf of the user. Right now we only had one layer. At the best that we got, we had one layer that is exposed by the API gateway. And there are several ways for that. We have seen before macaroons and biscuits. These are cryptographic ways where you can take a token and change it, attenuate it. But most people cannot use these solutions due to either lack of support or them being too complex. So you need to have another way of doing that with more simpler tokens. And we can do this approach even with stateful tokens. All we need is to have some API. So the idea, the things that we want is that the services will not be able to impersonate every user, and that they cannot use functionality that they do not need. So we can limit, for instance, scopes or permissions on the token. And the services can authenticate to one another. And the general method is to have something that is called a secure token service. This has existed for a long time in enterprise authentication standard. You had that with Kerberos, and you had that with SAML, and you had that with Windows Active Directory, but it wasn't used for app-to-app or service-to-service authentication in the web until recently. And is a standard that is part of that is called token exchange. And the idea is that you just add one more option to the token endpoint where you can send an existing token, an access token that you have, for instance, and replace it, exchange it for another token. And you specify something that is called an audience. So this way, Auth finally supports multiple resource server. You say, I want to have a token for another audience. I am service A. This is my access token. This is the authentication proof that I am service A. This is another thing that you can provide. I want an access token that I can use to call service B. And with this approach, we can implement service-to-service communication. Thank you, everyone. I would have wanted to have more time to go deeply into that, but yeah, this is what we have in the current app.
Okay, thank you both.
Thank you.
Thank you for the nice presentation.